Welcome to this module, and in the last module what we have seen? We have seen how we can use resistor and capacitors along with operational amplifier to form the oscillators, right. And we have seen two kinds of oscillator, one is your phase shift oscillator and another one was your Wien bridge oscillator. Now, if I want to operate or if I want to use the circuit in a high frequency range from 200 kilohertz to few gigahertz, can I use the similar RC phase shift oscillators or Wien bridge oscillators? I may not. I may not be able to use those oscillators at high frequency. So, in the application when you are asked that we have to design an oscillator which can be used for at or at a higher frequency, what you will do? What you will do? You have to design an oscillator using LC, using inductor and a capacitor. So, how does an inductor and capacitor help us, and how does the use of inductor and capacitor along with op amp will help us to form a LC oscillators, and then we will see the type of LC oscillators as well. Okay. So, let us see what are the LC oscillators. If you see the screen, what you will see that the oscillators which uses the elements L, that is inductor, and C, that is capacitor, to produce oscillations are called LC oscillators. Very easy definition, right. Now, the circuit uses or using L and C is also called tank circuit, right. It is also called tank circuit or oscillatory circuit, tank circuit or oscillatory circuit, which is an important part of LC oscillator. Okay. This circuit is also referred as resonance circuit or tuned circuit. That is why LC oscillators are also called tuned oscillators, tank oscillators, resonance circuits. They have the circuit that is a feedback circuit is a LC circuit. These oscillators are used, you see, at higher frequency from 200 kilohertz up to few gigahertz. Due to high frequency range, these oscillators are often used for sources of radio frequency energy. Okay. So, now you know that what kind of oscillators can be used for RF energy. We can say that the oscillator like LC oscillators can be used to understand or to if I know the LC oscillators, I can use as a source for RF energy. Okay. I can use LC oscillators as a source for RF energy. Okay. So, as we have discussed, LC tank circuit consists of L and C connected in parallel as shown in figure, you can see here, right. Now, how does this works? Okay. How does this work? So, initially let us consider that when we apply the DC source, the capacitor is charged with polarities as shown in figure, right. Now, you can see here the video, right. When the capacitor gets charged, the energy gets stored in the capacitor as electrostatic charge. Okay. We will see how this what exactly this is happening in this particular video here, we will see later. Okay. Right now, you focus on the first line, even this video is distracting you from focusing, try to focus. There is another exercise that when we are learning, when we are understanding something, our focus should be completely on what we are learning and not to other things. So, if I am saying that let us focus on the slide, we should not focus on this particular video. Let us see how many of you can do that. Okay. Okay. So, where were we? We were that when the capacitor gets charged, right, the energy gets stored in the form of electrostatic energy. When such a charged capacitor is connected across the inductor in a tank circuit, the capacitor starts discharging. So, what will happen if there is a capacitor which is charged, and if I connect the capacitor to an inductor, what will happen? It will start discharging. it will start discharging. So, if you see the screen, that is what is written when a capacitor is connected across inductor, right, the capacitor starts discharging through inductor as shown. The arrow indicates the direction of flow of conventional current. The arrow will indicate the directional of the conventional current. Due to such current flow, the magnetic field gets set up around the inductor, and thus inductor starts storing the energy. So, what we are saying is capacitor will start discharging, inductor will start charging. When the capacitor is fully discharged, maximum current flows through the circuit, correct. Initially the capacitor was charged, now the capacitor is discharging through the inductor, and the inductor got charged and the capacitor is discharged. At that instant, all the electrostatic energy is stored as the magnetic energy. Why magnetic energy? Because now the energy is converted into the inductor. Initially there was capacitor, it was charged, this charging is called electrostatic energy. Now, if I connect a capacitor or in series or in a fashion with the inductor, what will happen, that the charge in the capacitor, this will start discharging and inductor will start. So, assume that this pen is a inductor, these two fingers that I am showing it to you, the thumb and a index finger, these are capacitor plates. Now, capacitor plates are fully charged. When you connect the inductor with the capacitor, this plate will charge, the capacitor will start discharging and inductor will start storing the charge, right, inductor will start storing the charge. So, this electrostatic energy is converted to magnetic energy, the electrostatic energy is converted to magnetic energy, alright. This is easy, this is what is shown in the figure. So, let us come back to the screen, and what we will see here is, you see here, if you see initially the capacitor is red, where you see when the plus is here, you see here, right. So, when there are plus like this, you see, okay, you can see here 1 2 3 and that is it, correct. So, when there is plus here, that will be minus here, you see this one, can you see this? When you see that, you will see that maximum electrostatic energy is there. Now, when you have connected inductor, when you connect an inductor, the capacitor will start discharging and the inductor will start charging, that is what is shown here. Initially capacitor is charged, now inductor is charged, now inductor starts discharging and capacitor will start charging in a reverse direction, we will see here, you see. So, what we have seen, capacitor is charged initially with plates in this particular fashion, right, then it is connected to a inductor. So, what will happen, the capacitor will start discharging and inductor will start charging. So, magnetic energy is there, right, this is what is shown here. Now, once this is there, the magnetic field will start collapsing, and we should know a law called Lenz's law. Lenz's law, as per the Lenz's law, this starts charging the capacitor with the opposite polarity, making longer plate positive and upper plate as negative, making the lower plate as positive and upper plate as negative. So, what does it say? This is the first condition, right. Now, the inductor is charged and capacitor is discharged. So, we have to remove the charge from the capacitor because it is now discharged. Now, what will happen? Now, this magnetic field that is there in the inductor, this one, that will start collapsing and the it will start discharging and capacitor will start charging, but in a reverse polarity because of the Lenz's law, right. So, now it is charged like this and inductor is completely discharged, which you can see here, right, or you can see here in the circuit when it is, when the inductor is discharging, capacitor is charging, but now it is a reverse way, right. So, after some time capacitor fully gets charged with opposite polarities as compared to the initial polarities. Initial polarities were that this capacitor was having positive polarity like this, upper plate, and lower plate was negative. In this case it is reverse. So, the capacitor gets fully charged with the opposite polarities, right. The entire magnetic energy gets converted back to the electrostatic energy in the capacitor, correct. So, when the inductor starts discharging, the entire magnetic energy would be again converted back to the electrostatic energy, entire magnetic energy will be converted back to the electrostatic energy. Now, what will happen? Now, capacitor again starts discharging through the inductor. See, so beautiful. First capacitor charge, then is discharge, inductor charge, the inductor discharge, capacitor charge, then capacitor discharge, again inductor charge. This goes on continuously, right. So, but the direction of the current again through the circuit is now opposite, and again the electrostatic charge is converted to the magnetic charge. When the capacitor is fully discharged, the magnetic field starts collapsing, charging the capacitor again in the opposite polarity or opposite direction. So, what will happen? Thus, the capacitor charges with alternate polarities and discharges, producing alternate current in that circuit, right. It charges, it discharges, it charges, sorry, it charges, discharges, charges, discharges, charges, discharges, charges, discharges, like this. Now, one thing you may have seen, which is shown here, that there is oscillation, right. See, but they are dying, right. You see here, oscillations are dying, right. That is why, because every time when energy is transferred from capacitor to inductor and back from inductor to capacitor, there is a loss due to which the amplitude of oscillations of current keeps on decreasing every time when energy transfer takes place. You see here, it keeps on decreasing. Hence, actually we get exponential decay, right, oscillations called damped oscillations. This we have seen, right, there are damped oscillations. So, this is a damped oscillations. Such oscillations would stop after some time. Such oscillations will stop after some time. So, now we know why there is oscillation, we know why there is alternating current, because of charging and discharging of the capacitor and inductor simultaneously and in opposite polarity. So, capacitor is positive, then capacitor will charge in the negative polarity upper plate, then again it will discharge, inductor will charge storing magnetic energy, in magnetic energy collapses, electrostatic energy again comes into picture because capacitor again charges with opposite polarity. So, this goes on continuously, but whenever there is a charge transfer, there is a loss of energy, and subsequently you will see that the oscillations will start decaying. So, if it starts decaying, we cannot have oscillator because it will stop, right. Oscillator is something that can have sustained oscillation, not decaying oscillation, not amplified oscillation, sustained oscillation for long time. But in this particular case, what we have seen that LC oscillator in this particular case, okay, the damping is called damping, right, it is dying. So, what we can do to save it, or we can generate again the similar kind of waveform. Let us not let the signal die. If we do not want the signal to die, what we can do? Let us see in the figure. Let us see here in the slide. In LC transistor amplifier supplies this loss, LC oscillator, a transistor amplifier or a op amp supplies this loss of energy at proper times. The care of the proper polarity is taken by the feedback network. That means that whatever the loss was there, that can be taken care of by using the amplifier circuit, right, by using the amplifier circuit. Thus, LC circuit or LC tank circuit along with amplifier can be used to obtain oscillations called LC oscillators. Okay. So, LC plus amplifier will be called LC oscillator. Due to supply of energy which is lost, the oscillation gets maintained, hence sustained oscillations or undamped oscillations are formed. The frequency of oscillation generated by LC tank circuit is, the frequency generated by LC will depend on what? It will depend on inductor and it will depend on the capacitor, right. So, here our formula would be instead of 1 by 2 pi r square c square, right. We do not write like this, right, here, because there is no R c. What we write here? We write 1 by 2 pi under root of L c, right, where L is in Henry and C is in L is in Henry and C is in farad. Depending on type of tank or circuit used, LC oscillators are classified as Colpitts or Hartley oscillator. Okay. So, if once I know the function of oscillator, the function of LC oscillator, I can use the LC oscillator in two different ways. One is called Colpitts oscillator, one is called Hartley oscillator. So, we have to see what is a Colpitts oscillator, what is a Hartley oscillator, we will see later. First, let us see the basic LC oscillator and the feedback network, and let us see how it works. So, in this particular circuit, what we are looking at, the LC tuned circuit forms a feedback network, while an op amp or FET or BJT can be active devices in the amplifier stage, right. So, the figure shows a basic form of LC oscillator with the gain of the amplifier as AV. Okay. So, gain of this particular amplifier, right, is AV. The amplifier output feeds the network consisting of Z1, Z2, Z3. This is your feedback network. We will assume that active device with infinite input impedance such as FET or op amp, then the basic circuit can be replaced by linear equivalent circuit as shown in the figure. It is a linear equivalent circuit, is very simple, input impedance extremely high, then you have gain, then you have output impedance low, and then you have feedback network which is Z1, Z2 and Z3, right. We are talking about this particular circuit. So, amplifier produces a phase shift of 180 degree because it is a inverting, while the feedback network provides additional phase shift of 180 degree to satisfy the required condition for the oscillation. Okay. So, let us see or let us analyze the amplifier stage. Let us analyze the amplifier stage. Okay. So, what we see here, as the input impedance of the amplifier is infinite, there is no current flowing towards the input terminals, right. As the input impedance of the amplifier is infinite, no current will flow towards input terminals, that we know. So, let RO be the output impedance which is shown here of the amplifier stage, as I equals to 0, Z1 and Z3 appears in series, right. See here, because I is 0, it looks like Z1 and Z3 are in series, right, while combination in parallel with Z2. So, Z1 Z3 looks as if they are in series with combination of Z2 in parallel, correct. This is what is written here. This equivalent circuit is ZL. So, Z1 Z3 in series with Z2 we call as ZL. Okay. We have Z1 Z3 in series with Z2 . This combination we call ZL. Okay. Now, I is what? I is nothing but minus AVI upon RO by ZL, RO plus ZL, and VO is nothing but I into ZL, right. So, from these two equations, what will be gain? Gain is nothing but VO by VI equals to minus AV ZL divided by RO plus ZL, where A is the gain of the amplifier stage, right. Very easy to determine this. So, if I want to do analysis of the feedback stage, so let us consider that now I have feedback stage Z1, Z3 and Z2. So, for the feedback beta calculation, let us consider the circuit which is shown here from the voltage division in parallel. Here I see, you see here, right. What will I have? It looks like Vf by Vo is nothing but Vf by Vo is nothing but Z1 plus Z1 divided by Z1 plus Z3. But Vf by Vo is what? Vf by Vo is nothing but your beta. So, beta equals to Vi by Vo, right. Phase shift is 180 degree. So, beta is Vi by Vo is minus Z1 by Z1 plus Z3. So, A into beta if I want to write, then I can write the formula A from here, right, AV into ZL divided by RO plus ZL, right, which is here into beta. So, this can be nothing but this is required loop gain, ZL can be written as Z1 plus Z3 parallel to Z2, right. ZL can be written as Z1 plus Z3 parallel to Z2. This is how the feedback stage analysis can be done. This is how the feedback stage analysis can be done. Now, we have not finished it. We have not finished the feedback stage analysis. Let us see further. Okay, let us see further. So, after substituting value of ZL, we have to further simplify. For further simplification, we will get A beta equals to this value. Now, here Z1, Z2 and Z3 are what? Reactive components, because they are either L, Z1 and Z1, Z2, Z3 either L or they are C. That means, they are reactive components, right, reactive elements. So, Z1 is j omega x1, Z2 is j omega x2, Z3 is j omega x3. So, where x is nothing but L omega, or x can be minus 1 by omega c, right. For capacitive reactance, for inductance we know it is a omega L. So, to have a phase shift of 180 degree, the imaginary part of the denominator must be 0, right. So, imaginary part of the denominator is 0, then we can have x1 plus x2 plus x3 equals to 0, right, and A beta is value which is here. So, what we will have? We have, you see, AV equals, this is same equation A into beta, just we have replaced Z1, Z2, Z3 by x1, x2, x3. So, but x1 plus x3 equal to x2, right. Therefore, minus A beta will be equal to minus AV by x2. So, minus A beta we will get, we will derive AV into x1 by x2, correct. If x1 plus x3 equal to minus x2, we can have a minus A beta equals to AV into x1 by x2. So, in this particular case, according to Barker-Crescent criteria, minus A beta must be positive and must be greater than or equal to unity, right. As AV is positive, minus AB will be also positive, because AV is positive here, right. Only x1 and x2 will have same sign, while x3 will have a different sign, right. This indicates that your x1 and x2 can be same capacity, same reactive element, but x3 should be different than the x1 and then x1 and x2. Okay. So, this indicates x1 and x2 must be of same type of reactances, either both inductive or both capacitive. While the equation, from the equation what we have seen previously, what we have seen, x3 equals to minus x1 plus x2 must be inductive if x1 and x2 are capacitive, while x3 must be capacitive if x1 and x2 are inductive. So, what we understood is, what we understand here is that if I have a reactances, if I have value of x1, x2 and x3, and if I select x1 and x2 to be capacitor, then my x3 can be inductor. If I have x1 and x2 to be inductor, my x3 would be capacitor. Okay. So, this is what we have to remember in case of the LC oscillator using LC oscillator circuit. And what we understand from here is, if I have x1 x2 equal to L, x1 and x2 equal to L and x3 equal to C, then it will be my Hartley oscillator. Hartley oscillator. If I have x1 and x2 equal to C and x3 equal to L, then I will have Colpitts oscillator. Then I will have Colpitts oscillator. All right. So, depending on the reactances element in the tank circuit, we can determine whether it is Hartley oscillator or Colpitts oscillator. Okay. So, let us see, now let us see Hartley oscillator, and then we will go to the Colpitts oscillator. All right. So, what exactly Hartley oscillator is? Now, we have seen LC oscillator, and we understood that how LC oscillator works, but using LC oscillator, if we have two inductors, that is X1 and X2 is our inductor and X3 is a capacitor, then it becomes an Hartley oscillator. So, in case of Hartley oscillator, what is the circuit and how does it work? If it is a Colpitts oscillator, you see you have to again be little bit smart. If you do not remember in exam how many capacitor Hartley was using and Hartley oscillator we have used, how many inductors in Colpitts oscillator we have used. So, we think like this, okay. It is a easy way of understanding, remembering. Colpitts starts with what? C, right. Colpitts starts with C, we have two capacitors. We have two capacitors and one inductor. Opposite is Hartley, one inductor, two inductors, one capacitor, right. So, now I do not forget between Hartley and Colpitts, because I know that this is a trick, it is a trick to remember, will not work everywhere, will not work every time, but in case if you do not remember, it is a trick to remember how many capacitors can be used, how many inductors can be used. If there are two capacitors, it will be Colpitts oscillator, right, start with C. If there are two inductors, it will be Hartley oscillator. It does not start with L, but I am just giving you an example to remember quickly Colpitts oscillator. So, anyway, let us see Hartley oscillator and how does it work. Okay. So, the Hartley oscillator is one of the classical LC feedback circuits and used to generate high frequency waveforms or signals, alright. This can be implemented by using different circuit configuration. The major part of Hartley oscillator are the amplifier section and the tank section. Of course, it is amplifier section and the tank section. The tank section consists of two inductors, you see two inductors and one capacitor, that is your Hartley oscillator. Okay. Each section produces a phase shift of 180 degree of the AC voltage and hence it produces a sine wave. So, this is the tank circuit, you can see two inductors, one capacitor, right. This is an inverting amplifier, that means that my output would be 180 degree out of phase with respect to input. That is why this LC oscillator will help me to again provide a phase shift of 180 degree. So, here my output would be 180 degree out of phase with respect to input, right, with respect to input, and that is why this LC oscillator, when I feed this 180 degree out of phase, it will make again in phase with the input signal. Okay. This is what its circuit is. Inductor mounted on the same core, you can see here, and the output voltage you will see the oscillations happening. So, a sine wave generated by feedback circuit is coupled with the op amp circuit, we have seen that. Then this wave is stabilized and inverted by the amplifier. The frequency oscillator is varied by using the capacitor in the tank circuit, keeping the feedback ratio and the amplitude of the constant, output constant for the frequency over a range of frequencies. So, what is that? The capacitor right can be used for varying the frequency of the oscillator, and the feedback ratio and the amplitude of the output is constant, right, for a frequency over a frequency range. Now, frequency how it is given? It is given by FO equals to 1 by 2 pi under root of L equivalent into C, right, because there are L1 and L2. What is L equivalent? L equivalent can be L1 plus L2 plus 2M or L1 plus L2. Right. To generate oscillation from this circuit, amplifier gain must be selected greater than or equal to the ratio of the two inductors, right. So, AV can be greater than or equal to L1 by L2, correct. If the mutual inductance exists, between inductor L1 and L2 because of the common core for these two coils, then the gain will become L1 plus M divided by L2 plus M. Now, what is mutual inductance? Guys, you have to understand, you have to learn, alright. There were something Lenz's law, you have to understand, you have to learn, right, learn by yourself, right. How when you use inductors, how come mutual inductance comes into picture and how the equation comes into picture, you have to understand. Okay. So, this is how the gain of the amplifier can be determined in case of the Hartley oscillator. So, let us solve a problem. and this circuit is taken from electronicshubs.org. So, consider the figure in which Hartley oscillator is constructed with operation amplifier and feedback LC, right, feedback LC. By referring the given values, determine the operating frequency and maximum acceptable value of resistance R for the oscillations to start. Okay. So, what we are asked? We are asked to find the value of R, we are asked to find the value of the frequency, operating frequency, right. So, we know operating frequency is given by 1 by 2 pi under root of L equivalent into C, where L equivalent is L 1 plus L 2, L 1 is given 0.1 Henry, L 2 is given L 1 is given 1 micro Henry, L 2 is given 0.1 micro Henry. So, we substitute the value of L 1 and L 2 and we get L equivalent equals to 1.1 into 10 raised to minus 6, right. Now, capacitor is given, yes. So, let us substitute the value F O equals to 2 pi under root of L equivalent into C. So, 4.799 megahertz, you see. Now, feedback factor. What is feedback factor? Feedback factor is nothing but L 1 divided by L 2. So, what is L 1? L 1 is 1 into 10 raised to minus 6 because it is 1 micro Henry. What is L 2? L 2 is 0.1 micro Henry. So, 0.1 into 10 raised to minus 6. So, answer would be 0.1, right. Therefore, the minimum gain required would be 10, right. Minimum gain required would be 10. Now, you see it is an inverting amplifier. So, we have R 2 by R. What is R 2? This one, right. So, my gain would be R 2 by R. So, what is R 2? 100 kilo ohm, right. What is my R? I do not know, right, and gain should be equal to 10. So, 10 would be equal to 100 K by R, or R would be nothing but 100 into 10 to the power 3. So, in terms of ohms divided by 10, or that will give me 10 into 10 to the power 3, or R equal to 10 kilo ohms, R equal to 10 kilo ohms, right. This is what we have found here, R equals to 10 kilo ohm here, right. So, very easy to solve the problem for the Hartley oscillator. So, what are the advantages of Hartley oscillators using op amps? Okay. Why we have to use op amp based Hartley oscillator? So, instead of two separate coils as L 1 and L 2, a single coil of bare wire can be used and the coil grounded at any desired point along it. So, that is the advantage, right. So, using L 1 and L 2 separately, we can use a single bare wire. By using variable capacitor or by making core movable, frequency of oscillators can be varied, correct. The amplitude of the output remains constant over working frequency range, that is very big advantage. Very few components are needed, including either two fixed inductors or a taped coil. But there are some drawbacks also. So, what are drawbacks? Drawbacks is it cannot be used as lower frequency. You can see the frequency that we derived just in the previous case 4.9 megahertz, right. We have seen that it is about 200 kilohertz and above, or megahertz and above to some gigahertz. So, it is a high frequency, right, it is a high frequency oscillator. So, it cannot be used at low frequency, since value of inductors become large and size of inductors becomes bulky, correct. The harmonic content in the output of this oscillator is very high, hence it is not suitable for the application which requires the pure sine wave. So, the harmonic component in the output signal would be so high that we cannot use when we have application where sine wave, very pure sine wave is required, pure sine wave is required. Okay. So, that is another disadvantage or a drawback of the Hartley oscillator. Now, if we have seen a Hartley oscillator, then we can also see Colpitts oscillator. Why? Because in Hartley oscillator we have two inductors, one capacitor. Colpitts oscillator, two capacitors, one inductor. You see this circuit, two capacitors, one inductor. This is called tank circuit. What is called? Tank circuit. Okay. So, what is a Colpitts oscillator? A Colpitts oscillator is an LC oscillator which uses two capacitive reactances and one inductive reactance in the feedback network. Okay. So, LC oscillator is nothing but oscillator in which 2 capacitive reactance and 1 inductive reactance in the feedback network is, that is tank circuit, is called Colpitts oscillator. The op amp provides the basic amplification needed, while the feedback network is responsible for setting the oscillator frequency. Correct? Feedback network, this feedback network is responsible for the oscillator frequency, right, and this particular network op amp is nothing but a amplifier. So, it will provide the amplification. Now in the given circuit, the op amp is connected as an inverting amplifier with a high gain as compared with the transistor circuit. So, we have not seen transistor circuit, so forget about it, but the op amp here has a high gain. The LC network is placed in positive feedback, as you can see, right, and of the operation amplifier. Another point is, when the power supply is given to the circuit, there is no signal, but the small noise voltage are amplified by the op amp. This makes the both capacitor to start charging and discharging. Right. When power is given, the capacitor will start charging and discharging, right, with the help of the noise voltage, because these noise voltage are amplified and they are provided back to the feedback network from here, right, and this will cause the capacitor to charge, charging and discharging. The part of signal across capacitor C2, right, or this one is fed to the inverting amplifier. It is then amplified and keeps the network oscillating strongly. Easy, very easy, right. Here the frequency is given by FO 1 by 2 pi L C equivalent. In case of Hartley, 1 by 2 pi L equivalent into C, right. So, in that case L equivalent was L1 plus L2 plus 2m or L1 plus L2, right, L1 plus L2. But in case of Colpitts oscillator, the C equivalent will be nothing but C1 C2 divided by C1 plus C2, correct. So, what are the applications of Colpitts oscillator? Let us see. Application of Colpitts oscillator are, Colpitts oscillators are used for high frequency range and high frequency stability. Second, a surface acoustical wave or SAW resonator, which when we want to have SAW resonator, we can use Colpitts oscillator. Microwave applications, very high frequency applications, mobile and communication systems, right. These are used in chaotic circuits which are capable to generate oscillation from audio frequency range to the optical band. The application areas includes broadband communication, spectrum spreading, signal masking, etc. Right. So, the application of oscillator, Colpitts oscillators are in several areas from SAW to microwave to mobile communication to spectrum spreading and so on and so forth. Okay. So, this is how we can design the Colpitts oscillator using LC. So, guys, what we have seen in this module? What we have seen in this module? What we have seen is how we can design an Colpitts oscillator and how we can design a Hartley oscillator using a tank circuit. So, whether we have to use 2L or whether we have to use 2C and 1L or 2L and 1C, that depends on the type of circuit that we are designing. In case of Hartley oscillator, it will be 2L 1C. In terms of Colpitts oscillator, it will be 2C and 1L. Alright. So, this is about this particular module. In the next module, what we will see? We will see how we can design another kind of oscillator, that is your crystal oscillator, very stable oscillator, okay, crystal oscillator. So, look at this particular module, understand how the Colpitts oscillator and the Hartley oscillator can be used, in principle how the LC oscillators can be designed, and let us see in the next module crystal oscillators, and then we will move forward. So, I will see you in the next module, and till then you take care, have fun.